Okay, welcome to lab here. So as I mentioned in lecture, we're going to kind of continue on lecturing here and sort of wrap up hopefully this chapter. We're going to do maybe another example and finish up what's left of this sort of chapter. All right, so we've been talking about really stoichiometry and some different ways to do stoichiometry type problems. We did some titration problems, which is solution stoichiometry. We sort of did a problem there where we figured out how much mass is going to come from a problem where we started with molarity and volume. And hopefully, as you could sort of see in those examples, really they are the same steps in a basic stoichiometry problem that you do, those same sort of 4 steps where you want to balance the equation, you want to convert to moles, you want to do the mole to mole relationship, and then you want to figure out whatever you're looking for at the end. Again, the major difference a lot of times is sort of how we get to moles. So instead of sort of in a traditional stoichiometry problem where we convert grams to moles using the molar mass, here we're using molarity and volume and to get the moles, and then sort of continue on in the same fashion. We also saw that at the end, instead of a lot of times going back from moles to grams, we can use molarity on the back end of the calculation to figure out things like molarity, like in that last example we did. We can also use the molarity and the moles to figure out the volume in some of those other examples that we did. So just to sort of finish up the little topic here about sort of stoichiometry and solution stoichiometry before we get to the rest of sort of what's in the chapter. I want to talk about what happens when we have sort of a situation in terms of stoichiometry similar to what we saw when we were talking about basic stoichiometry problems. So let's take a look at an example like this one here. Let's say we wanted to calculate the mass. So calculate the mass of calcium carbonate solid that forms when 25 milliliters of 0.1 molar calcium nitrate solution is mixed with 20 milliliters of 0.15 molar sodium carbonate solution. Okay. So we're looking for the mass of our product that is going to be produced. And so you may say, well, it seems very similar to maybe that first one that we did. So let's approach it the same way. We, again, like any stoichiometry one, going to need an equation. So that's going to be our calcium nitrate going to react with our sodium carbonate. And hopefully also as well, you can see it's a double replacement reaction. And again, our sodium is going to end up with our nitrate. So we want to use the proper formula there, which is going to be NaNO3, NaNO3, plus 1 minus 1. We then want to put together our calcium, which has a +2 charge, with our carbonate that has a -2 charge. So that's going to give us our CaCO3. That's going to be our solid. So again, we want to start with our correct formulas. We want to make sure that we also balance it. So in this case, we do need a 2 here, I believe. And that would then need a 2, no, got the carbonate 1, so that should do it, I think. So 1 calcium, 2 nitrates, 2 sodiums, and 1 carbonate. So we would be balanced in this case. Now, if we sort of go through the information like we did before, ultimately in this case, we want to get over here to grams of our calcium carbonate. And we are starting with, for calcium nitrate, 25 milliliters and 0.1 molar. We are mixing it with 20 milliliters of 0.15 molar of this guy. Now, kind of like what we've been doing, if we look at this information here, I have both the volume and the molarity here. And because I have the volume and molarity, like we saw in those previous examples, that is going to allow us to get to moles. When I look at the other reactant, I also have volume and molarity, which is going to also allow me to get to moles as well. So the key on that is you are able to get to moles of each of the reactants. So that means that this technically is a limiting reagent problem, right? Because just like what we talked about when we did regular stoichiometry, we're actually able to get to moles of each of these guys, which means we need to figure out which one's the limiting reagent. And that's sort of the key, right? You have the starting amount of both reactants, and you need to figure that out. So even in sort of a solution stoichiometry problem, if you still have enough information to get moles of each of the reactants, you still need to figure out the limiting reagent. So we do need to kind of approach it maybe slightly different than what we were doing, but kind of similar. We're still going to really start out with the moles of each of these. So I'm going to figure out the moles of calcium nitrate. And that is going to be our 0.025 liters, which is our 25 milliliters converted into liters. We're going to use the molarity there, which is 0.1 moles per liter of our calcium nitrate. And that will get me 0.025 times 0.1 gives me 0.0025 moles of calcium nitrate. Now, because we could also do that for our other reactant, we're going to do that as well. So the moles of sodium carbonate will be, same deal, we're going to convert our milliliters into liters, 0.02 liters. Going to use the molarity there to get our moles, so 0.15 moles per liter. And that will get us 0.003 moles of sodium carbonate. So again, hopefully you could see that we've now converted it into our moles of each of these. So we do need to figure out the limiting reagent. So we could do this problem just like we've done the other one. So you could do an ice table. You could do it your other way if you like to do it some different way. But we'll continue on to figure out the limiting reagent. So again, here we had our calcium nitrate plus our sodium carbonate, giving us our sodium nitrate and our calcium carbonate. And again, here we had a 2 there, I believe. Okay, so I'm going to do it the ice table way. Again, you could do it your other way if you choose. So remember, initially here, we'll take the moles of our calcium nitrate, which is 0.0025. Take our moles of our sodium carbonate, which was 0.003 moles. This is going to be 0. This is going to be 0. Change here would be minus x plus 2x and x, which means at equilibrium, 0.0025 minus x, 0.003 minus x, 2x, and x in this case. First off, any questions on the ICE table there? Again, similar to what we did previously. Remember that in order to determine which one is our limiting reagent, we need to set each of these guys equal to 0 and solve for x, which in this case makes it pretty simple. X in this case would equal 0.0025 moles. X in this case would equal 0.003 moles. Again, here we are looking for the smaller number, which would be our limiting reagent. So we could see that this guy here is our smaller number, which means this is not the correct value for X. And this would be the limiting reagent, which in this case would be our calcium nitrate. By default, the excess reagent would be our sodium carbonate. Now, the nice thing about this, as we've been talking about, is we're actually interested in this guy. And we could see from our table that at the end, the calcium carbonate equals X. So that means that the moles of calcium carbonate equals X. And since X equals 0.0025 moles, that would be how many moles of calcium carbonate we would produce. That technically would be the theoretical yield in moles. But we're actually interested in it in grams, so we do need to go one more conversion. We need the molar mass of calcium carbonate. So calcium is 4008, carbon is 1201, and there's 3 oxygens at 16 each. Gets us a molar mass for this guy. The molar mass from the periodic table of calcium carbonate, something like 100.1 grams per mole. So the last step that we're going to do is kind of like step number 4 here. In this case, we actually are looking for grams. So we're going to take 0.0025 moles of calcium carbonate. We're going to use the molar mass from the periodic table and multiply it by it. The moles will cancel, and we will end up with 0.25 grams of calcium carbonate that would be produced. Again, this would be our theoretical yield. So sort of the same sort of process. Again, this is really step number 4. Up here is kind of step number 3, along with the figuring out the limiting reagents. And obviously step number 2 and 1 was the moles and the balanced equation. Any questions on any of those steps? So this illustrates a point. Sometimes people think, oh, we could only have limiting reagent problems that involves grams and stuff like that. It really isn't that. As you can see in this example, we had volume and molarity for each of those. So we're able to get the moles of each of the reactants. So again, that really is why I say, in order to sort of recognize a limiting reagent problem, the thing that you want to think about is, do I have enough information to get to moles of each of the reactants? So in this case, we did, and we would have to treat it as a limiting reagent problem, just like if we had grams of each of those to begin with, we would. And just so you know, you could even have a combination of those things. You could have one reagent where you have the molarity and the volume, which will allow you to get the moles. And the other reagent may just be in grams, which also would allow you to get the moles. And as we'll see when we get to something, for example, like gases, you could have enough information about the 2 reactants in a gas problem to actually get the moles for both of them and do a limiting reagent problem. So sometimes people think, oh, limiting reagents can only be strictly, when you're taking grams and grams, but it can be anything, because this is obviously 2 solutions you're dumping together, and you have enough information to do so. Any questions on now stoichiometry, limiting reagent, stoichiometry, any of that type of stuff. Okay. So then let's continue on with the rest of the stuff here. So we've been talking mainly about molarity, but there are other sort of concentration units that are used not instead of molarity, but in addition to molarity. One very common one here is a percent by mass. And this is sometimes what is referred to as percent mass to mass, and is sometimes abbreviated like this, percent M/M. M/M means mass to mass. And to figure out the percent mass to mass, that is the mass of the solute, so the smaller part of the solution, divided by the mass of the solution times 100. So this really is our percent mass to mass equation here. And people oftentimes will mess up on this bottom part here. The bottom part is the mass of the solution. And remember that as we talked about, a solution is really made up of two parts. It's made up of the solute, which is the smaller part, and the solvent, which is the larger part. So that's what this part is here. And it's very common in these sort of problems that people will only use the mass of the solvent on the bottom. And the reason that usually will occur is because in these type of problems, it is very common in the problem that they will separate the mass of the solute and the mass of the solvent into sort of two separate numbers. So sometimes people always just kind of look at the solvent and go, oh, that's the solution. But again, you want to make sure that you get both of those, the percentage of the mass of the solute plus the mass of the solvent. What that means is, for example, if I had a 4.5% mass to mass solution of sodium chloride, you could actually take this percentage and kind of convert it into a usable conversion factor. So usually when we have a percentage, we oftentimes will consider having 100% of something, right? So if we assume 100%, what that means is the numbers will remain the same. And what that would mean in this case is basically we have 4.5 grams of sodium chloride in 100 grams of solution. And you really could use this as a conversion factor. You could also flip it the other way around and go in 100 grams of solution, there should be 4.5 grams of sodium chloride. So sometimes it's easier to kind of do these problems as like a conversion factor type problem and kind of convert that percentage into like a usable sort of conversion factor. You could also just plug and chug into the equation and solve for everything as well. Now, in addition to percent mass to mass, there's also a couple of other percent sort of concentrations. There's percent volume to volume, like in alcohol. That is the volume of solute over the volume of solution times 100%. And this is basically milliliters over milliliters is usually how we sort of think about it. And for example, same sort of deal, if I had that 4.5% volume to volume sodium chloride solution, you could turn that into two usable conversion factors. You would say you would have 4.5 milliliters of sodium chloride and 100 milliliters of solution. Or in 100 milliliters of solution, you have 4.5 milliliters of sodium chloride. So again, you could kind of convert that into a usable sort of conversion factor. Unlike the mass to mass one, usually in a problem, they'll just straight up give you the volume of the solution. So you don't really have to worry too much about that. It's usually not broken apart or anything like that. So in that sort of sense, that one's a little bit easier. You just kind of plug and chug it into there. And sort of a third type of percentage type unit in terms of concentration is percent mass to volume, or percent M/V. And that is the mass of the solute divided by the volume of the solution times 100%. So this is essentially grams over milliliters, kind of like density, right? So grams over milliliters times 100%. Same deal as the others. If you have that 4.5% mass to volume sodium chloride solution, that would mean that you basically have 4.5 grams of sodium chloride in 100 milliliters of solution, or vice versa. You could use it the opposite way like we've been talking about. 100 milliliters of solution, 4.5 grams of sodium chloride. So percent mass to mass, or mass to mass percent, volume to volume percent, and mass to volume percent. These are very common units of concentration that are used as well. Again, usually not anywhere near how molarity is used. That is for sure the most common unit of concentration, but these are also very, I'll say, acceptable concentrations of units, or units that are used as well. And this is what I was talking about, just to tie it together with the dilution part that we were talking about. This is the part where instead of that M1V1 equals M2V2, people sometimes will use C1V1 equals C2V2. And again, in place of the molarity there, you could put any of these units in there as well: percent mass to mass, percent volume to volume, percent mass to volume on each side. As long as they're in the same units on both sides, again, you could kind of use that equation sort of generically for some other types of units. Any questions on that there? Okay. So let's take a look at one here. So since we got some of it here, let's talk about what's going on in this question here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. We want to calculate the percent, the mass percent, which is our mass of the solute divided by the mass of the solution times 100%. Now, when we look at this, remember that the calcium chloride here is going to be our solute, as it is the smaller part of the solution. The 50 grams, which is larger than 2.5, is our solvent in this case. So the mass of the calcium chloride is our solute, and the solvent here, though, is our water. So it is important in this case, like you see here, to get the actual mass of the solution, we need to take the solute plus the solvent gives us the mass of the solution, which is what we need here, right? So to figure out the mass percent, we want to take 2.5. We want to divide it by actually the 52.5 and times it by 100%. I will say this is a part where people will very commonly only divide by 50, which is just the solvent. And we end up with 4.76%. Now, since it is a percentage unit, there really is no units, so grams and grams technically cancel. But we do leave it as percentage, and usually we would indicate M/M to indicate that it is mass to mass percent we're talking about here, rather than say volume to volume or mass to volume sort of percent. And we would lay up something probably like calcium chloride here in terms of that. Any questions on that calculation there? So really the key with this one is you want to make sure that you get that full mass of the solution. All right, let's take a look here. There it is. So why don't you try this one? The concentrated hydrochloric acid solution contains 37.2% by mass hydrochloric acid. What mass of hydrochloric acid is contained in 35.5 grams of the concentrated hydrochloric acid solution? So see what you come up with. All right, so let's take a look and see. So now some people may be a little confused as to how I know like the 35.5 grams is the solution. So a couple of things to remind yourself that typically the name of the solution is the solute. So if I have a hydrochloric acid solution, the hydrochloric acid would be the solute, or the hydrogen chloride really, but the hydrochloric acid would be the solute here. Now, if I'm asked what is the mass of hydrochloric acid, that would tell me that I'm looking for the solute, because that obviously is the solute, which means by default, the 35.5 grams here would have to be the mass of the solution itself. So that's a good thing to remember. A couple of ways you could kind of solve this. You could really plug and chug into the equation there for mass to mass percent, which as we've seen is our mass of our solute divided by the mass of the solution times 100%. You could also do this as sort of a conversion factor problem, which sometimes might be a little easier to sort of visualize what's going on. So I'm going to do it that way. So if I have 37.2% mass to mass HCl, what that essentially means is I have 37.2 grams of HCl and 100 grams of solution. Or if I needed it, I could do it the opposite way, 100 grams of solution, 37.2 grams of HCl. So I know I'm starting with 35.5 grams of the solution. We want the solution to cancel out, so we want to use a conversion factor here on the left. And that would get me 37.2 grams of HCl, 100 grams of solution. Grams of solution will cancel, and we will end up with, what was that, 13.2, something like that. 13.2 grams of HCl. So if you sort of take the conversion factor approach, you get this sort of calculation. Truthfully, it is the exact same calculation you do if you plugged into this equation and rearranged it. You had the percentage, you had the mass of the solution, you would be solving for this guy. And if you did that, that would get you the mass of the solution, which is times the percent mass to mass, and divided by 100, which if you look over here mathematically, that's exactly what you did in this calculation. So it comes out the same. Again, just a little bit more forward there using the conversion factor sort of approach, but you do get the same answer, obviously, if you just plug and chug it in. Any questions on any of that there? Percentages, mass to mass, percent mass to volume, percent volume to volume. The other ones pretty much work the same way. You just kind of plug and chug in there what you need into those formulas. All right, so we've now seen a few different types of concentrations. We've seen molarity, which is sort of the really top one in terms of usage. We've seen percent mass to mass. We've seen percent mass to volume, percent volume to volume. And now here's a fourth, I guess, type of concentration unit. And this one is known as what is known as molality. And molality, not to be confused with molarity. So just for comparison purposes, again, molarity is moles per liter. That is big M. Molality is actually small m, which is not to be confused with mass. And that is moles of solute divided by kilograms of solvent. So there is a difference between these two things, and that is a major difference. So the molality is moles of solute over kilograms of solvent, sometimes referred to as molal. Is like molarity is molarity or molar, and this is molal. So again, little m, moles per kilogram of solvent, big M, moles of solute per liter of solution. So one is moles over kilograms, so moles over sort of mass. One is moles over volume. By the way, the thing that ties both of these together, if you ever needed to kind of go from one to the next, is actually density, is what usually will kind of tie these guys together and allow you to kind of convert from one to the next. So, you know, you could have come across a problem or may come across a problem somewhere along the way where it may be molality and molarity, and maybe convert from one to the next, or you have enough information to figure out, say, molality, but you want the molarity, and you could use density. Usually is that sort of bridging number that you need to kind of convert from one to the next. And just sort of roughly giving you sort of just unit wise, if you think about it, if you take molarity, moles per liter, and you take density and you divide by it and do grams per milliliter, right? And we convert those milliliters into liters. Milliliters cancel, right? Milliliters cancel, liters cancel, liters cancel. You're left with moles per gram, which then can be converted right into 1,000 grams in a kilogram, right? Grams cancel. You get down to moles per kilogram. So it's really that density piece that is usually the little thing that you need if you ever needed to go from sort of molarity to molality in terms of that conversion factor. Density is sort of that bridge that usually gaps those two. As you can just see looking at the units here, you can get yourself to one versus the other. Obviously, if you're here and want to go the other way, you kind of go backwards, right? And you go forward this way, right? Because this is molality here, and that is molarity over here. All right, little preview of something maybe to come in the later chapter. All right. So why don't you give this a go? We want to calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. Let me give you some numbers that will be helpful. Carbon is 12.01 from the periodic table. Hydrogen 1.008. And oxygen is 16. All right, so take a moment and see what you come up with in terms of the molality of this solution. Okay, so let's take a look. So we're in this case, again, not looking for molarity. We're looking for molality, which is little m. And again, that is moles of solute divided by kilograms of solvent. So a couple of things might be helpful to try to figure out, and hopefully you could figure this out. But water here would be our solvent. And for the most part, the thing you dissolve is usually your solute, and it's usually the smaller part, which it is in this case as well. So we definitely need to convert our grams here of our solute into moles. So we're going to need the molar mass to do that. And in terms of our water, which is our solvent, we need to get it to kilograms. But we have milliliters, but they also did give us the density of water. So using the density of water and the milliliters, since D is equal to M divided by V, I have the density of water, I have the volume of water. That's going to allow me to calculate the mass of the water. So using the density equation, mass is equal to volume times the density. The volume is 175 milliliters. The density is 1 gram per milliliter. Milliliters cancel. Gives me 175 grams of water, which is close to what we need, but we do need it in kilograms. So 1,000 grams in a kilogram. And that says 100. I'll put an extra 0 in there. Gives us 0.175 kilograms of water, which is our solvent. So we do have the bottom part here. We do need to get, like I said before, our grams of our C3H7OH into moles. So we're going to need some molar mass there. So that's going to be 3 times 1201 for carbon, plus 8 times 1.008 for all the hydrogens, plus 16 for the oxygen, gives us a molar mass of C3H7OH from the periodic table of 60.09 grams per mole. So we're going to do a basic conversion of taking our 61.7 grams of C3H7OH. We're going to use the molar mass again to convert it into moles, which is what we need for our formula. And that will get us, call it 1 point, we'll call it 1.03. And that is the moles of our solute. So now you can see we do have everything we need to solve for molality. So the molality would be our moles divided by our solvent in kilograms. And if we do that, we get something like 5.87. Now, the units here, again, could be one of two things, very much like molarity. We could leave it as moles per kilogram. Or you could say 5.87 little m, and you could put what it is if you like. So again, you could do it either way is perfectly acceptable in terms of the final answer there. Any questions on any of those steps there? So molality, again, is another unit of concentration. We will definitely see molality pop up a lot in a later chapter. I want to say it's chapter 11. We'll see a lot when we talk about what are known as colligative properties. So molality is used a lot in colligative properties, and those are things that are known as things like boiling point elevation, freezing point depression. The unit of molality is used a lot in that sort of calculation. So we definitely will kind of see this guy show up a little bit more in a later chapter. Again, I think it's maybe not 11, maybe it's 9. Is there 9 or 10? One of those, I think, is actually the right chapter. Any questions on that? Okay. Now, another, I don't want to say it's necessarily a concentration, but we'll sort of ish call it that. Another way that that's important relationship that we see, and we will actually see this in two places down the road. We will see mole fraction, and we will see mole fraction when we talk about gases, which is the next chapter. We will also see mole fraction again pop up also in that colligative properties that I was just talking about. So we'll actually see this mole fraction pop up a couple of places down the road after we talk about it here. And the mole fraction is basically the fraction of moles over the total number of moles. So it's the moles that you're interested in divided by the total number of moles. The difference is you don't multiply it by 1,000, not by 1,000, you don't multiply it by 100 to get a percentage. So this is sort of a percentage without the multiplication. So that's why the mole fraction equals 1, because we don't multiply it by 100 in this case. So really, to calculate the mole fraction, it's sometimes abbreviated with an X. So let's just say A. We want the mole fraction of moles of A. You take the moles of A divided by the total moles. And again, here we don't multiply by 100, so it's not a percentage. And that's why we'll get a point something number. And basically, that's why if you did have 100%, it would equal 1. Because 100% of point something is basically 1, right? So mole fraction, again, is sort of another way to represent, I won't say concentration, but I guess the concentration of moles, I suppose. But it is sort of used a lot in some calculations along the way. So why don't we try this one here? Calculate the mole fraction of methyl alcohol, which is CH3OH, in a solution that's composed of 0.328 moles of methyl alcohol, 0.929 moles of ethyl alcohol, or ethanol. So take a moment there and see what you come up with. Okay, so let's see here. We're looking for the mole fraction. So basically, we have basically a solution and floating in that solution. We have methanol and ethanol, basically. So we're looking really for, again, not really the percentage, but really the fraction of that solution that's made up of methanol here, or methyl alcohol. So the mole fraction of methyl alcohol would equal the moles of methyl alcohol divided by the total number of moles that are there. So again, here we're not going to multiply by 100 and make it a percentage. So the mole fraction of our methyl alcohol would equal the moles of our methyl alcohol, which is right here, 0.328 moles, divided by our total moles, which would be our methyl alcohol, plus the moles of our ethanol, which is 0.929 moles. And if we do that, 0.328 divided by 0.328 plus 0.929 gives us a mole fraction of 0.261. Again, not multiplying by 100, but essentially it's 26% made up of methyl alcohol, really, in that particular case. We could do the same calculation for the mole fraction of ethyl alcohol. It would look the same deal. For the ethyl alcohol, it would be the 0.29 moles divided by our total moles there, the 0.328 plus the 0.929. And if we did that, we get 0.739 as our mole fraction for our ethyl alcohol. So earlier it said, right, if you had 100%, it basically equals 1, right? If you had 100%, the mole fraction would equal 1. And that means that really at this point, we could have figured out the fraction of ethyl alcohol by taking 1 minus 0.261, and you will get there as well. And again, because we know those are the only two guys that are basically in there, that's going to represent 100%, and we could have just obviously subtracted 1 from that number, the first number, and figured out the other one. Question on mole fraction. So again, we would definitely see mole fraction in the gas chapter, next chapter, and we will definitely see it a little bit later on when we talk about colligative properties as well. Any questions on any of that there? That should wrap up this chapter here, I believe. Yep, that is it. Any questions on this chapter? Stoichiometry, molarity, molality, percent mass, volume, mole fraction, volume percentage. Any questions on anything? Okay, so a couple of things. As was sort of the question in lecture, tentatively speaking, right as of now, the exam is still scheduled for 1 week from today. It definitely will obviously cover everything through this chapter. We're going to be starting the gas chapter on Monday, so it's going to cover some of that gas for sure. Like I said, I am thinking about sort of options and what would be best, because we do have exam 4 coming up not too long after that. And believe it or not, we have our final coming up not too long after that as well. So I'm going to look and try to think about what might be the best option. Either keep it where it is, and maybe if we don't get far enough on Monday or Tuesday, cut off some of the material that will be on it, or maybe move it to Monday and complete the gas chapter. So I'm going to sort of reevaluate and think about it over the weekend, and also obviously reevaluate and see sort of where we are on Monday in terms of the gas chapter, which is technically supposed to be on there. So as of now, I would, if I were you, sort of consider it still on to go for next Thursday. I would use this weekend, obviously, to study, at least obviously through the material that we've covered. There's a good amount of material in here to cover. A reminder as well that the redox information is going to be on that exam, in addition to the redox stuff that we lectured on in lab, and we did that study assignment and the last experiment as well, the balancing redox in acidic and basic conditions. So that part of the stuff is going to be part of the material that potentially will show up on the exam as well. So keep that in mind. You do have probably a lot of stuff to sort of study with or study about, obviously, at this point. So I would definitely consider the exam still on for Thursday as of now. And I would study probably this weekend, you know, as it was going to occur on Thursday. Again, more definite information will be given on Monday, and it really is going to depend sort of on where we are in terms of material on Monday, and sort of where we end and stuff like that, just so you know. All right, any questions on that or anything like that? Okay, Officially for today, the experiment is study assignment G, which I think is our last study assignment of the season here. And it is on stoichiometry, which will be very good practice for you and review, hopefully, for the exam, because that material definitely is going to be on it. Since we did take up a lot of time here during lab for lecturing, I'm going to give you plenty of time to finish this one. So this one is going to be due officially on Monday. So at the end of lab on Monday, study assignment G will be due. That should give you plenty of time to finish it. And there should be a lot of practice on there. I think there's a lot of ones where you have to write some equations from words, balance them, do the stoichiometry. There should be maybe some solution stoichiometry in there as well, maybe some titration problems towards the end, some limiting reagent problems, some basic stoichiometry problems. So it should be a pretty good review in terms of stoichiometry. So officially, the box will be up there today if you want to turn it in anytime, obviously between now and Monday, but it will be due officially Monday at the end of lab. Yes, officially the lab from yesterday, which is experiment 9, I believe, is due today at the end of lab. So hopefully you watched that or have made a pretty good moment on that. If not, then you do need to make sure you turn in experiment 9, I believe it is today. Yeah. Study assignment F was due yesterday, so hopefully you turn that in. But today, experiment 9, the redox of iron, is due today. Study assignment G will be due on Monday. Any other questions on any of that? Okay, again, we're ending week 5. We're rolling on to week 6. Got 3 more weeks to go, right? That's 12 days. Yeah, almost down to 2 hands. We're almost there. But we're getting to the end. A lot going on in these last 3 weeks. We got 2 more exams to go and a final, obviously. We have some more experiments, some more formal lab. We're technically getting into next week, the big experiment of this class, which is the titration experiment, scheduled for like 4 days, really. There's 3 different parts with a lot of calculations, very similar to what we did today in lecture and those titration calculations, which is why I went into a few more examples of titration sort of calculations, just to make sure, hopefully, when we get there in the experiment, it should hopefully help you when we get there. Any questions on anything in terms of that? Well, congratulations on finishing, hopefully, the 6th week here, or the 5th week. We're going into the 6th week. Make sure, again, you do study as the exam is coming up, and you want to keep up on top of everything that's happening. So for the rest of the time, officially, you should be working on study assignment G. You should maybe be finishing up experiment 9 if you haven't. And you need to, let's see, you did that. And you need to, if you have any questions, feel free to ask me. And to answer your question, yes, I'll click the button so you can see that as to what went wrong there on the exam. I think I forgot to click that button. So I will click that button so you can see which ones were marked incorrect, I think, on the multiple choice and all that kind of stuff. Other questions on anything? Okay, so like usual, I'll be here for the rest of the time. If you have questions on anything, I'll be happy to answer. Otherwise, use this time wisely, obviously, to finish the experiment, start on the study assignment. Make sure you type here if you haven't done so already. Yeah, if you need the solubility rules, they will be provided for you. Probably on there. And like I said before, if not, then you can probably use the general thing, but I think the solubility rules will be provided for you. Kind of like how the electronegativity was provided for you. All right.